Okay, in this example, again, we have a variable parameter, and in this case, we have only variable f. Okay, there's a pile shown in this figure. It's drilled into soil and rests on the bedrock as shown. A load of P is applied on top of the pile along the length of the pile and around its perimeter. Soil supplies a constant frictional resistance W equals 3.7 kilonewton per meter. Determine the force Fb needed at base of the pile for equilibrium and the magnitude of the downward displacement at A relative to B. Right, the P, L, D, and the modulus of elasticity have been provided. Again, let's see how to solve it. Well, first of all, we have to use the integral methods. Right, so obviously, here we have constant E, and it's a no distribution. It's a cylinder, so the area is also a constant. So we have only F, and that is the distribution function. Okay, so again, this is vertical system. We'll need to use y, right? So delta equals integral 0 to L Fy over Ea dy. So this is the equation we will use. Okay, here the E is a constant, A is constant. We just need to determine Fy. So in the first step, we calculate the Fb. Right? Calculate Fb, so we do not need to use the integral. We just use a free body diagram to determine this. Right? So this is shown here. This is a free body diagram. Since we're asking you to determine Fb, so just cut it at the bottom. And we have known that the B is upward, right? So just Fy equals 0. So just Fb upward Fb plus the distributed frictional resistance. That is a 3.7 kilonewton per meter. Let's keep the kilonewton per meter times 5 meter, right? Times L minus P equals 0, right? So just Fb equals P minus 3.7 L. And the P is 75 kilonewton minus 3.7 kilonewton per meter times 5 meter. Okay, so this is 18.5. So the result will be 56.5 kilonewton. Okay, so we're done with the first question. Then the second, the magnitude of the downward displacement at A relative to B. Right, this is the downward deformation, the deformation of the overall AB actually. So we're calculating delta AB. Right, delta AB equals delta A. If we set that at point B it's a rigid point, so fixed, this bedrock cannot be compressed at all. Okay, so we're just calculating delta AB, right? Delta AB equals integral 0 to L Fy over Ea dy. Right? So then we will need another free body diagram to figure out what is Fy. This is to determine the distribution function of Fy. Okay, so we're calculating Fy. To do this, we need a free body diagram. Just first of all, we need to do integral. We need to set a original point at the beginning. So here we can set on top of it. On top of it, here is y equals 0 and y is downward. Okay. So let's cut a little piece of it. This is P on top of it and the point A. And from here to here, this is y. Right. So if you have, if we want to know like the Fy at here, applied to this dy, a little piece of dy here, right? And Fy can be added here, right? So based on this free body diagram, we have frictional resistance, right? Frictional resistance, that is W equals 3.7 kilonewton per meter or 3.7 newton per millimeter. Right, these are the same. And based on this, we can write a equilibrium equation that will be downward. We have upward, one upward, that is W. W times y, right? W times y minus P minus Fy equals 0. So Fy here equals Wy minus P. Right, let's use Newton. Okay, let's use Newton. So that will be 3.7 Newton per millimeter times y millimeter minus P is 75,000 Newton. Okay. This is our Fy. Right, it's so Fy equals 3.7 y minus 75,000, and the unit is Newton. Then apart from that, we have known like E. This is the one we'll need, and the E is what? The E is 8.3 GPa. That will be GPa, and we want to use MPa, so that would be 8,300 MPa. And the area A will be pi over 4 times d squared. The d is 100 millimeter square, so that would be 7,850 square millimeter. So we get everything in this equation, right? So we can rewrite this equation that we can get delta AB equals 0 to L Fy over EA dy, so that is 0 to L is 5 meter, and here since we're using millimeter MPa Newton, we're using this system, so 0 to 5,000. Fy there is 3.7 y minus 75,000 over 8,300 times 7,850 dy. Okay, so the rest of work would be math, right? Would be all math. Right here, just so we can get this constant out, and then inside of it will be 3.7 over 2 times y square minus 75,000 y. Then from 0 to 5,000, right? So this can be calculated. The result will be negative 5.04 millimeter. Okay, this has to be negative, since you're pushing on top of this pile. You're adding a p to push it, so this displacement of point A will be downward. This AB will be shortened. Right, so this negative sign is just reasonable.